Are you able to see my screen, and is it full screen, and can you hear me?
Yes, sir.
Okay, good.
Yes, sir.
So,
Sir, I had a question from last class. So,
yeah, go ahead.
um, so you had written that for the corona of these AGNs, their temperatures can go in tens of kV or hundreds of kV.
Yes.
So the X-ray emission that we see is majorly due to upscattering of UV photons or the thermal spectrum of the corona itself.
See, the corona is not called usually a thermal spectrum. Because it is not strictly a black body, because there has to be a mechanism by which energy is transferred to the corona. So even if it is due to without any upscattering, that is also referred to as non-thermal emission. So for example, in the case of the sun, there is very little upscattering. There isn't much to upscatter there. So in the case of the sun also, the solar corona emission is thought of as a non-thermal emission. It is not purely thermal. So it's not, the shape of the spectrum is not strictly a black body. The peak may be corresponding to the temperature. The peak may be similar, but if you plot the whole profile of the X-ray emission from the sun, it is non-thermal in nature. Its spectrum is not like that of a black body. So in that sense, it is non-thermal. So does that clarify?
Yes.
Yeah. So we don't refer to that coronal emission as non-thermal. As thermal. Coronal emission is referred to as non-thermal in be it the case of the sun or the case of the AGN corona. Okay, so this is where we had stopped the last time, and what we said is that we try to explain all the AGN properties from the viewpoint of AGN unification, and we went through all of these. This is another schematic view now of how we can think of the various kinds of AGN when thought of their properties along three axes. One is accretion rate, which, as we saw, largely determines the luminosity. Then the mass of the supermassive black hole. And third is the angular momentum of the supermassive black hole. And so these are the three axes which are shown here in this figure. And one second, let me try to write it. And if you think of radio quiet objects, they're basically low angular momentum black holes or accretion disks, and radio loud objects are high angular momentum accretion disks, and that is what is driving up the fountain of the jets and driving particles at high speed, relativistic speeds away from the nucleus. Seiferts, of course, now on this plane of the SMBH and accretion rate luminosity are all the radio quiet objects. We know that Seiferts are invariably hosted by spiral galaxies, and radio quiet QSOs are often hosted by elliptical galaxies. So if you think purely in terms of SMBH mass, the low mass supermassive black holes are sitting in spirals, and the high mass supermassive black holes are sitting in the ellipticals. Radio quiet QSOs are generally sitting in elliptical galaxies, although a few are present in spiral as well. We can also think of the variation along three other axes. Now we take variability as an axis, how much variability there is and how frequently does the flux vary. Again, like previously, we take the radio luminosity along one axis, and along the third axis, we take emission line width. And here we can arrange objects as sort of high emission line objects, which are the Seifert ones. and the type 2 AGNs, which are don't have high emission line widths because they're all narrow lines only. Those are the Seyfert-2s. Similarly, along the radio axis, you have the broad line radio galaxies and the narrow line radio galaxies and so on, right? You also have BL lacs, which are invariably very radioluminous and very, very highly variable. So they are on that plane, and they hardly show any emission line width. But as we saw the last time, the emission lines are there. They're just drowned by the Doppler boosting of the jet. So you don't see them very easily, but they're there. But you can think of it as BL lacs as lying on this plane of radio and variability with very few detectable emission lines. All combinations here are possible, except that there are no highly variable radio quiet objects. So the moment you see a AGN that is highly variable, and typically if it is variable at one frequency band, it will be variable in other frequency bands as well. There are no objects which vary except maybe in the radio. So because that's of the jet Doppler boosted variability. But if an object varies, say in the X-ray, it will also vary in the optical, right? It will also vary in infrared and so on. So there are no very highly variable radio quiet objects. They're all radio loud if they're variable. Okay, so this is how we can distinguish between radio loud and radio quiet using the spin parameter as the primary differentiator. And the spin parameter is defined as Cj over Gm square, and it has a maximum value of 1. That is the maximally spinning Kerr black hole. In the radio loud objects, wherever we've been able to measure the spin properties of the black hole, it seems to be maximally spinning. Okay, A's are always close to 1. In the radio quiet situation, it's much harder to measure the spin because very often I mean, you can still do it in the X-ray with the ion lines, but they typically have low spin accretion disks. Radio loud objects produce jets, and of course, radio quiet produce no jets. And here in the radio loud objects, the spectrum is dominated by thermal. And in the radio quiet objects, it is both thermal and non-thermal, okay? Which is what we just discussed a few minutes ago. The emission from the accretion disk itself is purely thermal, but the emission that is caused by let's say the X-ray corona, that is not thermal. It doesn't show a black body kind of shape. So it's a mix of both thermal and non-thermal emission, which is seen in radio quiet objects. Yes. AGNs with large radio structures, kiloparsec scale jets, are invariably hosted in elliptical galaxies. So this is an observation. This is an empirical observation that if you take any large radio galaxy with these kiloparsec or megaparsec scale radio jets and lobes, the traditional radio galaxies, if you look at the host of those galaxies, those host galaxy will invariably be elliptical. Any idea why this should be the case?
Due to the large velocity dispersion in elliptical galaxy.
Yes, you have large velocity dispersion in elliptical galaxy. You also have larger black holes in galaxies. But why is it that the jets that we see in elliptical hosted galaxies are not seen in spiral hosted galaxies? what can you say about the interstellar medium in elliptical galaxies and spiral galaxies? What is the difference? Which of them will contain a lot of gas in the interstellar medium?
Elliptical.
No, spirals. Okay, because ellipticals, remember, are supposed to be gas poor. They have exhausted all their gas. They've taken all their gas and converted it into stars at some early epoch. And if you look at the present day elliptical galaxy and try to look for gas in it, you won't find it. So if you use a radio observation to look for neutral hydrogen using the H1 emission line, you will not see H1 in elliptical galaxies, typically. Not all, but 90% of them or more. Whereas in spiral galaxies like the Milky Way, there is a lot of gas in the interstellar medium. So what can you therefore say about the baryonic density of the interstellar medium?
So it is low in elliptical galaxies and higher in
Correct. Absolutely. So the spirals have high density of baryons in the interstellar medium. And therefore, what will happen to the jet is that it will encounter a high density much more than when it is escaping from a elliptical galaxy. And when it encounters, that jet will be dispersed. You may form a hotspot, but that hotspot will be very close to the galaxy itself or within the galaxy itself in general. So we do see from Seyfert galaxies, for example, which are typically spirals, we do see kiloparsec scale radio emission, but we usually don't see well-defined jets, right? And in elliptical galaxies, there is nothing, there is no gas between the stars to stop the jet from plowing through the interstellar medium. There's nothing to stop the jet. So the jet just breaks out of the galaxy very, very easily. And then eventually somewhere it hits some overdensity and forms the hotspot and the lobes and so on. So such objects, although very rare, are not totally absent. So in 2012, Anand Hota and collaborators, Anand used to be a PhD student at NCRA many years ago. He found a special type of galaxy with the VLA and the GMRT. And here is a image, SDSS image of the galaxy. And this is not an elliptical galaxy. This turns out is a spiral galaxy. And therefore, that makes it very rare. And as you can see, the radio lobes are completely symmetric. They're very well defined. And they seem to be escaping from a galaxy which is a spiral. So this spiral galaxy must be special in some fashion. We don't know yet exactly what causes this phenomena. So some years ago, Veeresh Singh and collaborators, I was one of them, went and systematically looked for such objects. So we took the spiral galaxy catalog from the Sloan survey, and we took a large radio catalog, and we cross-matched them, and we checked systematically for hundreds of thousands of objects, whether they were double-lobed radio galaxies that were hosted by a spiral galaxy. And we found only a handful. We found about 6 objects. Today, there are, with a number of searches, there are only of the order of 20 galaxies which seem to be hosted by a spiral galaxy and yet show these large double-lobed AGN. This is really rare object, whereas we know hundreds of thousands of radio galaxies which are hosted by elliptical galaxies. So how do we find more of these objects? We find them by just systematic searches. in the radio and optical bands, and that's the only way to find them in a systematic way. Okay, so we saw in one of the earlier lectures that if you have a population of electrons with a power law distribution in energy, then it is the high energy electrons that lose flux, that lose energy faster, and therefore their flux goes down faster. So if you plot the spectral index, if you plot the flux density as a function of the observed frequency, you invariably find that initially it is somewhat less steep, but by the time you go to higher frequencies, it becomes more and more steep, right? Now, can we use this technique to find very distant radio galaxies? So this is an observation. This is an empirical observation again, that the spectrum is steeper at higher frequencies. So if you have a radio telescope and you want to discover candidate high redshift radio galaxies, can you use this fact in some way to select your sample? Yeah, any thoughts? Okay, so you can select it, because what will happen is, suppose you have a high redshift radio galaxy. Its high frequency spectrum will be redshifted to lower frequencies. So suppose it's at redshift 5, then the observed frequency will be 1/6 of the emitted frequency. So suppose it is emitting at 6 gigahertz, you will observe it at 1 gigahertz. Whereas for a nearby galaxy, you will observe 1 gigahertz emission at 1 gigahertz. So what will happen is the spectrum of that galaxy will, the redshift 5 galaxy will seem to you to be very steep. And you can use that fact to select. So by observing at 2 radio frequencies and computing the radio spectral index, you can identify galaxies that are very steep and therefore are likely to be at high redshift. This is not a very foolproof technique, because the variation with redshift is systematic, but there is also variation from object to object. There are some radio galaxies that have very steep spectra, and some others at the same redshift which don't have very steep spectra. So this is not a foolproof or highly efficient way of identifying very, very distant radio galaxies. You have to supplement this with other selection criteria. Okay. If you look at the luminosity function of radio sources in the radio bands, you will find that the luminosity function of AGN and star-forming galaxies is quite different, as you can see here. So what is shown here is the total power or the luminosity of the galaxy in watts per hertz. Okay, luminosity density for AGN and star-forming galaxies labeled by SF. And look at the data points again. Don't worry about those dotted lines and so on. Just look at the solid line and the data points. And as you can see, if you go to very high luminosities, you see invariably AGN. So at, let's say, a luminosity like this, the AGN are at least 10 times, so perhaps 100 times more numerous than the star-forming galaxies. But if you go below this luminosity, then the star-forming galaxies begin to take over, and the number of star-forming galaxies at very, very low luminosities dominates the luminosity function. Now, this will also translate into a corresponding situation when you look at it in terms of flux. There are star-forming galaxies at all redshifts. There are AGNs scattered around at all redshifts. And therefore, if you look at the the highest flux AGN in your, highest flux radio sources in your sample, they will invariably be AGN. So above about flux 1 gigahertz flux of about 100 millijansky, above that flux, there will be, above that flux density, there will be invariably AGN in your sample. As you go fainter and fainter, typically when you go below 1 millijansky in flux density, you will begin to encounter more and more star-forming galaxies. And if you go further down, let's say to microjansky levels, then the population will be dominated by star-forming galaxies. AGN are no longer important. Okay, so far we have followed a relatively uniform strategy for finding AGN, right? What do? We use some image selection criteria, maybe color cards, maybe something else, to identify candidate AGN. And then we go and measure their spectrum with a spectrograph, and the spectrum tells us whether they're AGN or not. Now the question is, can we do this with photometric data alone? Okay. This is an important question because gathering spectroscopy of any object is a very expensive exercise in terms of telescope time. So if you can do things with photometry alone, you can do things about maybe 100 to 1,000 times faster than you can do with spectroscopic techniques. So these are the kind of techniques that one can use. Mean colors, morphology, variability, astrometry. Okay, you can measure the positions and make sure they have zero proper motions, otherwise they're stars. And X-ray plus radio detections. So do multi-wavelength astronomy, multi-wavelength imaging astronomy in order to find and verify candidate AGN. So I just want to spend a few minutes just talking about the upcoming telescopes and large surveys that they will carry out that will greatly increase the number of AGN that we know of. And many of these are astrometric and photometric surveys. In terms of astrometry, there is a telescope in space right now, which is called Gaia. The purpose of Gaia is to carry out accurate photometry, but even more importantly, very, very accurate astrometry on more than 1 billion stars. These, of course, will be stars within the Milky Way, but the Gaia will also be able to detect a large number of AGN just by the fact that A, they're variable. Gaia is also a multi-epoch, carries out multi-epoch observations. So it observes the same part of the sky about 60-70 times through the survey. So AGN will be detected there through their variability and through the fact that there will be point-like sources and therefore part of the Gaia survey program, but yet not moving at all, whereas almost everything else is moving. Okay. Did you lose my screen for a moment? Because I got a message that you are now seeing my screen. Are you seeing my screen?
Yes, sir.
Yeah. Okay. In the optical, there is a new telescope that is coming up, a new observatory that has been built in Chile called the Vera Rubin Observatory. And they are carrying out a survey called LSST, Large Survey of Space and Time. And that is even more remarkable than Gaia, because Gaia is, I said, is going to survey every object maybe 60, 70, 80 times. LSST is going to survey the whole sky that is observable from its latitude once every 3 days. And it is going to do that continuously for 10 years and possibly more, because I'm sure the survey can be extended. This is a ground-based telescope based in Chile, almost ready. And within the next 2 years, it's supposed to get going. And what will it do? It will measure, it will basically take a photograph of the sky in 5 different broadband filters, all optical, of course, and keep on doing it continuously for 10 years. So if there is variability with any kind of time scale, if there's variability over a few hours, we'll find over a few seconds also we'll find it, because it'll take 2 exposures, one after the other. If it is variability over a few days, we'll again find it, because it will come back in 3 or 4 days. And of course, any multiple thereof, months, years, variability will be found. Thousands of AGN are expected to be detected in this way. You will need to verify that the AGN is not a star, not a variable star with some periodicity or no periodicity. You'll do that by obtaining photometric redshifts. So it is possible to obtain a rough redshift for an object by looking at its photometric properties alone through a technique known as the photometric redshift technique. And that will be done extensively with this new instrument. In the near infrared, there is now again a new telescope commissioned recently in the southern hemisphere called VISTA. It belongs to ESO. It is carrying out the VISTA hemisphere survey in the JHK bands. These will be very useful in trying to identify some candidate obscured AGN and so on. Next year, a new space mission called Euclid is supposed to launch, and that will carry out imaging of 15,000 square degrees in 3 near infrared bands, Y, J, and H. And that will also, because it's going to be space-based, the photometry will be very, very accurate. Again, one can try to combine that data with LSST data and get very accurate photometric redshifts. And some years into the future, there is a new infrared telescope that is to launch, which is called WFIRST. It will have the same kind of collecting area as the Hubble Space Telescope, but it will have a very wide field of view. That is its main strength. And it will operate at infrared wavelengths. In the radio, there are 2 new telescopes that have been finished recently. One is called MeerKAT and one is called ASCAP. And MeerKAT is in South Africa, ASCAP is in Australia. These 2 telescopes are carrying out very large continuum surveys in the radio bands, which will go to much higher sensitivity than the previous generation surveys carried out with the VLA and the GMRT and so on. Those will lead to new populations, new kinds of AGNs, as well as studies of AGN that over large redshift ranges, which is going to improve drastically, because these kind of surveys will find AGN at a range of redshifts. And by the end of the decade, the phase 1 of the Square Kilometer Array telescope should be completed. And when that happens, that will be another huge leap in the sensitivity, resolution, frequency coverage, spectral resolution, and many other properties of the telescope. And this is a very, very large international radio astronomy project, which will completely change things, but this won't happen till the 2030s. For X-ray astronomy, remember AGN, many AGN emit strongly in the X-rays, and most X-ray sources are AGN. There is a new telescope called eRosita, which was launched in 2019, and is expected to carry out a 7-year survey during which it will detect about 3 million AGN. All of these things imply that the data volumes are going to be very large, because these surveys are very large projects. They will generate terabytes and terabytes, and in some cases petabytes and petabytes of data. And therefore, it may become difficult to find AGN or find this. I mean, we will reach a stage where there won't be enough people to look at the images and see whether that's an AGN or. We've not yet reached that stage with spectra, but with massively multiplexed spectral surveys, we will reach that stage also within the next 5 years, where we won't have enough humans to look at the spectra that we are obtaining. So machine learning techniques, automated techniques are going to play a fairly important role in the coming years. Okay, so now during the rest of the talk, yeah.
So what about JWST for infrared observations?
Yes, so JWST was not included here because these are all surveys listed here will cover fairly large areas of the sky. JWST will of course be very crucial for follow-up observations. So let us say that with LSST or Vista Hemisphere survey, we find some very interesting object, and we want to follow that up with JWST, we can do that. So JWST will be not a discovery machine, but more of a follow-up machine, because it has a very narrow field of view. Like it's bigger than the Hubble Space Telescope, but not much bigger. It only sees a very small part of the sky at a time. So it is useful for once you have identified an interesting object that you want to study in detail, that is where JWST will play an important role. Okay, so I'm just going to cover a few topics which I feel I've not covered, or I've covered in very little detail. So this is going to be a bit of a hodgepodge over the next 20 minutes. So now, if you want to detect AGN efficiently, which means that you want to have a sort of near 100% guarantee that an object is an AGN before you even take the spectrum, right? Then X-ray techniques or X-ray imaging becomes a very powerful technique. So what is shown here on the left panel is an optical galaxy. It's a large galaxy, but the AGN is probably not that strong. It is not standing out as a point source at the center. So if I showed you a picture, just an optical picture, and asked you whether this is an AGN, you will say, I don't know. Okay, then maybe it's not a strong AGN, but it could well be a weak AGN. But now if I show you a 2 to 10 soft X-ray image, bang at the center, you see emission. Okay, and this is coming from your accretion disk and the accretion disk corona. And you'll say, yes, this is probably an AGN. And then, of course, this exercise has been done for many, many galaxies. And people have then gone and got spectrum of these objects. And if there is X-ray emission at the center, these invariably turn out to be AGN, except, so the only AGN that will be missed here will be the Compton thick AGNs, where the dusty torus is so optically thick that it's optically thick even to X-ray photons, and nothing can escape. So only those kind of very small number of type 2 AGN will be missed by this kind of selection technique. You can generalize this to large surveys as well. So over the last 25 years, a number of small regions of the sky have been studied in great detail at many different wavebands. So there will be optical observations, infrared observations, X-ray observations of the same part of the sky. And one of them, one of the earliest, in fact, is something known as HDF North, because there was later on an HDF South, Hubble Deep Field. And this was a very deep observation carried out with the WIFPEC camera on board the WIFPEC 2 camera on board the Hubble Space Telescope. So what you see here on the left panel is a color image made by combining several filters in which the Hubble has observed. And it turns out there are about 3,000 optical sources that are seen. Of course, you're not seeing all of them in this image. But if you go investigate the image in detail, you will find that there are 3,000 objects. At these faint levels, they're not stars, but they're actually, most of them, not all, but a very large fraction of them are galaxies. Now, if you ask the question, how many of these are AGN? And one easy way to answer it is to go and take an X-ray image of the same part of the sky. So this is the edge of the WIFPEC 2 camera. And this is an image obtained with the Hubble of the Hubble Deep Field North with a X-ray telescope, the Chandra X-ray telescope. And in place of 3,000 in this part of the sky, X-ray found 21 X-ray sources. And they're all AGNs. So at high redshifts, we cannot spatially resolve the AGN light from the host galaxy starlight. There is no way we can separate like we did for Seyfert's at low redshifts, or even at moderate redshifts with the HST where the quasar host galaxy was visible. So here you can't see anything, right? You just see it like a star. It looks like a point source in the optical. But the moment that point source coincides with a point source in the X-ray, then you can make the claim that this is likely to be a AGN. So people who are interested in AGN, what they did was they took this optical image, they compared it with the X-ray, they got these 21 X-ray sources and first got a spectrum of all of those galaxies. And then most of them turned out to be AGN. So the efficiency of selection was very high in the X-ray bands. What about the gamma ray sky? So this is an image of the whole sky obtained with a gamma ray satellite called Fermi, the Fermi Space Telescope. So it observed the whole sky for 2 years and constructed this all sky map, again plotted as often is in galactic coordinates. So you can see a lot of gamma ray emission from the disk of the galaxy. Okay, and this is basically caused by supernovae having gone off at different parts of the disk, which are left behind supernova remnants, which themselves shine in gamma rays. But also there are shocks which reaccelerate electrons to very, very high velocities. And these can then give rise to gamma ray emission. So this is gamma ray emission driven by star formation in the plane of the disk. If you go away from the disk of our galaxy, then you begin to see a few point sources. You can see some here, 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 right? And most of these point sources turn out to be AGN. There are a few pulsars, particularly binary pulsars, which have an accretion disk, etc., which can also generate gamma ray emission because they also have jets and so on. But most of them are not pulsars. Most of them are active galaxies. So how and what kind of active galaxies? Any idea what kind of active galaxies should emit strongly at gamma rays? Here's the answer. Okay. So if you look at the gamma ray sky, individual point sources, okay, there are of course supernova remnants, some pulsars and so on. There are a number of objects that we don't know. Okay, that's about 1/3. So one clearly needs to understand a lot more. But amongst the objects that have been detected, more than 50% are actually blazars. And that is not surprising, because what is happening with blazars? Blazars have their jet pointed directly towards you. So in addition to the Doppler amplification of the flux, there is going to be a blue shift of the overall radiation. And if the gamma factors are high enough, then some of these blazars, not all, will show emission in the gamma rays. And this is exactly what we see in the gamma ray surface. Okay, but gamma ray astronomy can be done from space, but can be done in a sort of indirect way from the ground as well. These high energy gamma rays, if they hit the Earth's atmosphere, they get absorbed, and these high energy photons can produce electron-positron pairs. And this can lead to a cascade of particles, which will, as they move through the atmosphere at very high speeds, give rise to emission, blue UV and blue emission, known as Cherenkov radiation. It's very faint, but it's bright enough to be detected whenever a very, very high energy gamma ray hits the top of the atmosphere. This is a picture of a new gamma ray telescope, Cherenkov experiment, atmospheric Cherenkov experiment, which is being built. And in fact, I took this photo in 2018 when I was there. But now last year it was completed, and round about now the telescope should start functioning and looking for flashes of Cherenkov radiation coming from high energy gamma rays entering the Earth's atmosphere. So this is not really an astronomy project. Most of this kind of work is done by cosmic ray scientists who are interested in studying cosmic ray showers. This has been a long tradition at TIFR. So this and the DAE, of course. So this telescope is built by the Bhabha Atomic Research Center. And here you see some telescopes of a smaller experiment, again an atmospheric Cherenkov experiment called Hagar, which was built about a decade back, again by the BARC guys. And this is the same site that houses the Mount Saraswati and the optical telescope, 2-meter optical telescope built by the Indian Institute of Astrophysics. In fact, I've taken it from top of Mount Saraswati. One interesting fact about this gamma ray instrument is that it is powered by solar panels. And you see those solar panels here and some more solar panels here all around the telescope. You can do another experiment, another kind of experiment, which is to, instead of looking for flashes of light, try to detect the fast moving charged particles as they move of the cosmic ray shower as they hit the Earth. And that is done via scintillation counters. And at UT, again, this is a TIFR facility from the Department of High Energy Physics, wherein they've set up this experiment called GRAPES. And I believe this is GRAPES version 3. And inside each of these sort of tin sheds is a scintillation counter. So how does the scintillation counter work? What the scintillation counter does is that whenever whenever a high energy particle comes through, they use a photomultiplier tube to create a cascade of particles. And eventually these protons or electrons or whatever the charged particle is that's come through, it generates a voltage, generates a current through the resistor, and it generates a voltage across the resistor, which is measured. So that's the basic idea. You detect charged particles by amplifying them in a photomultiplier tube. Okay, this is similar to operation of a charge coupled device, wherein you generate a photoelectron. You have a photon which comes in, which generates a photoelectron, which is then amplified and stored in the charge coupled device. Okay. This AGN can produce very, very high energy cosmic rays as well. These are referred to as ultra high energy cosmic rays. They have 10 raised to 18 electron volt of energy or more. These are very rare, but these also, just like the high energy gamma ray photons, these particles cause air showers, which again can be detected with atmospheric Cherenkov experiments and on ground detectors. So the most energetic particles, cosmic rays, can have energies higher than 10 raised to 20 electron volts. And this is equivalent to a cricket ball traveling at a speed as thrown by a very fast bowler, coming from a single particle. Okay, that particle may be a proton, or it may be a heavier nucleus of some other atom. There is some evidence that the high energy cosmic rays may be iron nuclei rather than protons. These are moving. If you calculate the Lorentz factor for these particles, it is very, very high. These objects are very, very close to the speed of light. And in fact, I read somewhere yesterday that if you send one of these particles and you send a photon alongside, after 200,000 years, these objects, the photon will be about a centimeter ahead. That is the kind of speed they go. So for all practical purposes, these are particles traveling at the speed of light. Now, where do these particles originate? That unfortunately is a much trickier question, whether they originate from AGN or from some other sort of exotic process in the universe. We don't know. But what we do know is that they cannot be coming from more than about 100 megaparsecs away. Because if they were, the chance of them encountering a thick piece of matter, thick enough, dense enough piece of matter that they create a cosmic ray shower and dissipate is very high. Therefore, these are not coming from very high redshifts. So people have been attempting to localize the particles and the photons coming from at very high energies, trying to see if they can map these to AGN. And they're trying to, there has been some success, but this is not a very difficult exercise. We can't be very sure, but there are claims in the literature that Centaurus A, which is one of the bright AGN in our neighborhood, is a source for a large fraction of these ultra-high energy cosmic rays. So this by itself is a different field. It's not really astrophysics. It's mostly particle physics who are interested in these cosmic rays, because they can study the properties of cosmic rays at very high energies, which they cannot do with the particle accelerators. So for context, the Large Hadron Collider produces particles with an energy of 10 tera electron volt, so 10 raised to 13 volts. And these particles are more than a million times more energetic. So we are not going to produce accelerators of that energy scale anytime soon. So till then, the cosmic accelerator is the best way of studying high energy particles and their properties. Okay. So one more sort of unrelated tidbit is trying to measure polarization in the accretion disk. So this is an image that was published a couple of months ago. It's a polarization map with the Event Horizon telescope of the black hole at the center of the M87 galaxies. And what they've been able to do is by actually carrying out full polar observations in the high radio bands in which they, high frequency radio bands that they operate in, they've been actually able to construct a polarization map of the region surrounding the thing. And the fact that you see these lines of polarized emission, these indicate, of course, the direction of the magnetic field lines, and the fact that we are able to see it and it is ordered, it's not random, indicates that A, there is strong magnetization of the accretion disk, and B, the magnetic field is ordered on very large scales. It's not random, it's ordered, and the magnetic field strengths can be estimated, and there are a lot of papers now that describe that, which is, they claim it's strong enough to push back on the hot gas and help it resist gravity's pull. And this may be one of the mechanisms by which not all the particles falling towards the black hole end up in the black hole. A fairly large fraction end up in the jet. And M87 indeed has a very large optical, X-ray and radio jet. These particles may be channeled out of the accretion disk due to the presence of a very strong magnetic field, exactly as predicted by the Blandford-Janek model. Okay, so this is now, and again, a sort of summary slide of the various kinds of AGNs and what their properties are. Okay, so we have radio loud quasars, radio quiet quasars, and so on. And these are only the major categories. The subcategories of objects are not listed here. But as you can see, it's a fairly complex table. And even if you say yes, no, weak and strong, etc., there is a lot of variety. But as we have seen with the unification model, increasingly data seem to suggest that the fundamental structure of the unified scheme is correct, and the variations that you see are due to some exceptional sources. For example, like those spiral galaxies which host an AGN. There are exceptions to the rule, but there are a very large number of objects that seem to follow the expectations that we have from the scheme of the unification scheme. Yesterday, when I was thinking about today's lecture, I realized that there are some topics that I have missed out covering. One major field of research today is in AGN winds, which means outflows from AGN. We talked of outflows from in the form of the jet, but there are also winds which are non-jet outflows, and we didn't cover them at all. Then there is a category of quasars called broad absorption line quasars. Normally we associate emission lines with quasars, but there are some quasars that have absorption lines. They're invariably radio quiet objects, so I did not discuss those. In studies of obscured AGN, the type 2 AGN, there have been a lot of recent developments made using data from the ALMA telescope, which helps us find molecular gas in the obscured AGN. I talked about dust in obscured AGN, but I didn't cover the molecular gas properties of the dusty torus. I don't think I covered high redshift AGN in enough detail, and the implications they have to galaxy evolution. I also mentioned numerical simulations several times, but there is a lot of work that is being done with numerical simulations. So I think that is something that I should have covered in greater detail. The mass buildup of the supermassive black hole is another topic that we did not cover. It's related to the high redshift AGN and their properties. So I will cover those. I'm sure that if you guys think about it, and if you, as you study AGN, you will find more things that I missed out during the course. And these are small enough topics that I could have easily fitted them in into the course. So if I teach the course again next year or later, I will incorporate all of these. So this slide was merely to gather my thoughts. So if any of you feel that I have not covered some aspects in sufficient detail, please send me an email, and I will be sure to incorporate that in the next time I teach this course. Okay, so I will end with this slide. This is from the book, from the Sasuke lecture course that I mentioned in my list of books. Okay. So in Switzerland, at a place called Sasuke, every year they organize a school on a specific topic. And in 1990, they organized one on active galactic nuclei. And they invite only 3 lecturers every time to come and give a set of lectures. So every lecturer gives maybe about 10 lectures each. And then they publish the lectures as articles in a book. So, of course, it's on a different topic every time. All the Sasuke lectures are generally in physics, not always in astronomy. But there are a lot of interesting Sasuke courses that have been taught over the last many years. So this is from that. So Roger Blandford, who was a pioneer in the AGN jets, he lectured at this school, and he in his article has published this particular image or figure. And he said, basically, AGN have phenomenology, or things that you can observe, phenomena that you can observe at all scales, going all the way from a megaparsec to about 10 parsec. On a megaparsec scale, we saw that you see all these powerful jets. Sometimes they're weak, sometimes they're strong, sometimes they're one-sided, sometimes they're two-sided. These strong jets produce hotspots where they hit the ambient medium. They can also create weak bow shocks where the lobe is expanding outwards. On 100 kiloparsec scales, you often see evidences of ongoing galaxy mergers or interactions in the AGN. You may see cooling flows and tidal flows and etc. At 10 kiloparsec scales, you begin to see the whole galaxy as a whole. You can see the AGN at the center. If there is a captured companion which is falling in, you'll be able to see that. On the 1 kiloparsec scale, you begin to see the dense molecular clouds that are present near the central regions. Perhaps there is a bar which is channeling gas towards the center and feeding the black hole. On 100 parsec scales, you see the familiar features of the AGN spectrum. You see the narrow lines coming from the narrow line region. You begin to see the continuum emission from the accretion disk and accretion disk corona, and you see this sort of extended accretion disk. In the 1990s, the concept of the torus had not become as popular as it is now, primarily because we didn't have at that time X-ray and infrared observations that helped us map the density and other properties of the torus. So for Blandford, this is basically just a large accretion disk, which extends outwards. It sort of thickens out outwards, but it's still thought of as an extended accretion disk. If you zoom in on 10 parsec type of scales, you see the beginnings of the jet. You see the inner part of the accretion disk. You see relativistic shocks, which are compressing the material in the jet and causing it to emit strongly than in other regions. And you see, of course, very strong continuum emission coming from the center. And you also see the broadline clouds that surround the central black hole. I don't quite understand what he means by stellar core over here in the stellar cusp. I'll have to go and read the article carefully to understand that. Okay, so I decided to end with this slide because this sort of summarizes the whole story in one picture that we've tried to cover in 14 lectures. So I would really appreciate feedback. I've taught this course for the first time. I've also taught a course, entire course online for the first time in my life. So it's a very new experience for me. So if you have any ideas, suggestions that will help me improve the next time, please, I'll be happy to receive them. Right? You can even send them to me later in case you're worried that this may affect your grade, etc. It won't. But in case you're worried, you can send it to me after I send you the grade. Okay, just write it down somewhere and then send it to me a month from now. Okay, so before we close, I'll make some announcements, and then if there are any questions on this or any of the other lectures, we can take them. So I've sent you the email that we fixed the 29th as the date. There are many of you have now responded. I think I've got about 8 or 9 emails from people stating what paper they want to work on. Unfortunately, we have at least 2 clashes, which means there are 4 people who have selected only 2 papers between them. So I will over email try to resolve that over the next couple of days. I'll write to these people individually and ask them, the simplest solution is one of them chooses a different paper. But if they're both insistent, no, they want to do that paper itself, then I'll choose a paper that is very similar to the paper they've selected. So those who have not responded, please respond. Remember, your assignment 1 is due on the 11th of June. Again, for that, I'll send you an email on how to submit it. Most likely, I'm going to ask you to submit it to in the NCRA office, in the NCRA secretariat, which is where the director and the dean sit. There are a couple of secretaries who sit outside, and I can ask them to, since they're there all the time, you can submit it. But I'll send you email instructions closer to the deadline. The second assignment I've started working on. I will put it out by the middle of next week, and then you will have again 2.5 weeks or maybe 3 weeks if you want a longer time to submit it. And so that will also come in towards the end of the month, will be the due date. So that's about it. So 2 assignments and your seminar, which will be the criteria for the bulk of your grade. I'm going to put in those 10 marks for class participation because several of you have answered many questions, so they can expect to get a good grade there. That's it. So are there any questions about the assignments and the seminar, or about the contents of the lectures themselves? You've been able to hear me, right?
Yes, sir.
Yes, sir.
Yes. Otherwise, I'm just speaking and no response indicates, I don't know. Anyway. So if there are no questions, we will close the last lecture and with it the teaching component of this course. And we will of course meet each other online on the 29th of June.
Thank you.
Hello. Yeah. Does anyone have a question?